Okay, right on the dot. I have a lot to get through, so I will start on time today. I'll try and finish by 10 to 11 for a break, yeah. So yesterday we went through the construction of the standard cosmology. Today we are going to go to the early universe, which as you'll see is much simpler because it's basically equilibrium thermodynamics. And then in this lecture, the meaning of this Ouroboros symbol will become clear. So the first thing we need to ask when we want to construct a model for the early universe is, do we know that the laws that we measure in the laboratory and that we are so confident about actually hold when we go back billions of years in time, billions of light years away, etc. So this is not a silly question because you could imagine that the laws of physics are the result of some evolutionary history and they have not always been the same. So we have to have some empirical probe of this. And one way is to actually probe whether the fundamental constants that we have today are the same in the past. And what this shows is a measure of the fine structure constant, which, as the name suggests, determines the splitting of spectral lines. And people have been trying to measure this fine structure constant as a function of redshift. So this is the look back time. So essentially people have looked back to nearly the beginning of the universe because you can study this in quasar absorption systems to a redshift of 3, 4, something like that. Here, 4, that is the highest point. And you see that the measurement is within the current value to within few parts in 10 to the 5. Now, actually the authors of this is Webb from Australia, they were trying to see if there was a time variation, and maybe you could argue that there was some slight deviation from this blue line, which is no change at all. But that is arguable because as you will see later, we can actually constrain that alpha was the same value as today to within a few percent at a redshift of 10 to the 12 at nucleosynthesis. So I can't think of any time dependence that would allow you to sort of fit a regression line here, which would not be far too much by 10 to the 12. But I think you will agree that this kind of is empirical evidence that things have been more or less constant. So therefore, we can actually proceed. So we can extrapolate our laws. Now, this is just food for thought. You could imagine loopholes in this, and in fact, in string theory, the values of all the couplings are meant to be expectation values of some moduli fields or something. What this is saying is that if they were doing their thing, they should have done it back in the past, not today. So now it's very straightforward. We have the Friedmann equation and we have the conservation laws for number of particles and for energy. So this just says that as the universe, the scale factor stretches, particles get diluted as you'd expect for something carrying a conserved quantum number, and therefore the energy density scales as redshift cube. And so now when you look at the Friedmann equation, we don't have a curvature term because that is going as 1 by a squared, so it is negligible in the early universe when everything else is going as a cube or a4 or faster. So we have dropped the lambda term that is negligible in the early universe. Already at the time of recombination, it is at least 10 to the 9 times smaller than the matter energy density because the matter energy density is going as z cubed. So by redshift of 1000, it is 1000 cubed times bigger. So therefore you have the Einstein de Sitter solution, scale factor goes as t to the 2/3. For radiation, the energy density conservation is got one extra factor of a because of course photons are redshifted as the expansion continues. And so now you have a z to the 4 factor, and therefore radiation will come to dominate over all other components as you go to the early universe. That's what makes life so simple. And note that the scale factor, if you want to write it in the same way, now is going as t to the half, and the energy density now goes as 1 by t squared. Now this actually is true whether you are in matter domination or radiation domination. Rho always goes as 1 by t squared, right? And we can define some scale factor at which the radiation and the energy density of matter come to be equal. So that is best seen pictorially. Matter, I said, is going as 1 by a cube, radiation is going by m by a4, they clearly cross at this point, and the scale factor then compared to today is always 1 by definition, is about 10 to the minus 4. The scale factor was 10, the universe, if you like, was 10,000 times smaller at the time of matter radiation equality. And today this is where we are, and there is supposed to also have been this lambda that has come through, and you can see from here that it was completely negligible compared to the other components at early times, and that then raises this famous why now problem, because this, if you try to evaluate this in quantum field theory, for example, in the standard model, you would expect a value of order a few hundred GeV to the 4th power, whereas what we infer, so what we actually measure from the data that were discussed in the last lecture is the lambda term that enters into the luminosity distance or the angular diameter distance. That turns out to be of order h naught square. This is not an energy density. This has got dimensions, as you see, of energy square. H naught in energy units, if you said h bar c equal to 1, is 10 to the minus 42 GeV, right? 10 to the minus 33 EV. So it's an infrared scale. It's the scale of the universe, the size of the universe, 10 to the 28 centimeters. To convert it into an energy density, I have to multiply it by 8, divide it by 8 pi g, which is basically multiplying it by Planck mass square. So h naught square is 10 to the minus 42, this is 10 to the 19, and therefore the geometric mean of those is 10 to the minus 12 GeV, or 10 to the minus 3 EV. And that is said to be the scale of the dark energy, but we don't actually measure this thing. What we measure is that we are inferring it, we are interpreting it as dark energy. Okay, so these things are important because even professionals in the field sometimes forget these things. We don't actually directly measure any energy density. We measure only this, infer it from the Hubble diagram of supernovae and so on. So as I said, that creates this why now problem, but we won't dwell in that today. Today we are going to go back to the early universe, and this is a picture that you would have seen, which traces the history of the universe back from the beginning till today. And it's basically on a log scale, which amplifies the early parts, because in terms of time, the early universe that you're going to talk about was a tiny fraction of the whole length of time. Okay, but most of the time, from the point of particle physics, nothing was happening. So in order to glorify our business, we put it prominently so that most of this picture is now taken over by particle cosmology, right, which extends from the Planck epoch, when the energy was of order the Planck scale, 10 to the 18, 10 to the 19 GeV, and that's a time scale of 10 to the minus 43 seconds. And we don't know anything about that. There is a conjectured grand unification scale of 10 to the 16 GeV. This is slightly out of date. It should say 10 to the 16. And that corresponds to a time of order 10 to the minus 35 seconds. It is conjectured because we have no direct evidence of grand unification, for example, of nucleon decay. Although the running of the couplings at low energy, as you know, as measured precisely at LEP, indicated that there should be unification around this scale, but we have had no direct evidence of that. Then there is this electroweak phase transition, which we now know is not a phase transition at all, it's a crossover, but this is when the Higgs mechanism occurred. That's where particles got masses, W and Z in particular. And much later, at 10 to the minus 8 seconds, there was the transition between free gas of quarks and gluons into confined objects, chiral symmetry breaking. That is also not a phase transition, that's a crossover. And after that, we come to the epoch of nucleosynthesis, which I'll discuss in the next lecture. That's at about 1 second, nuclear energies, MeV. And from this point onwards, we understand what's going on, because we can measure the elements synthesized there. We can talk about, that ends at the famous 3 minutes, and then we can talk about the recombination, or rather combination, of the primordial plasma to become the neutral universe that we subsequently inherited. That's at about a few 100,000 years, when the temperature is of order electron volt. and then structure formation, etc., up to today. Now, up to here, we can have direct probes. Beyond this point, we have a theory up to here. We don't have direct probes, except that there are relics of the early universe, and there are at least 3 relics that we need to understand. One is that we are made out of baryons, and we don't see any antibaryons, so you have to account for that baryon asymmetry. We have to account for dark matter, which we expect decoupled. Many models it decouples, as Tracy discussed, somewhere around here at about the 20th of the mass. So you're talking about TeV, up to TeV mass particles. It was around here. Of course, it could have been much earlier. Axions, as she discussed, actually were formed more at 10 to the 10, 11 GeV, although they only got their mass at the quark-hadron transition. And then there is also a very important relic, which are the density fluctuations, which created the large-scale structure that we see in the universe today. Because you can easily work out that if you just had a gas with Poisson fluctuations of the particles in it, those fluctuations are quite inadequate in amplitude to create structure. Okay? You need primordial fluctuations created on top of the just random statistical fluctuations in a gas. Now that we don't really know where those came from. We have a paradigm, I think is the best word for it, called inflation, which can generate it from some evolution of some scalar field or so on. But the point is that these things are for real. We have to account for these. We have a lot of interest in the baryon asymmetry. As yet, we have no definite picture. The most likely possibility, you are pursuing that it has something to do with the fact that neutrinos have masses. You can have then a process called leptogenesis, because in the standard model, leptons and baryons have equal footing, and baryon minus lepton number is exactly conserved. So you can create asymmetries in either baryons or leptons, which will be converted into the other. So this is our broad picture, but I'm going to focus today just on this part here, right? So there is a lot more to talk about, and maybe in future schools we'll discuss baryogenesis and inflation and so on. Now I want to start by, many of you have heard these things before, and so you're saying, okay, the same old stuff. Well, I want to throw out a few things here and there to hopefully make you sit up and think a bit. So one question that I put here is, very basic. We are talking about an universe. We are, presumptuous enough to talk about the entire universe. Does the universe have any net quantum numbers, right? So, for example, we can ask the question of the contents that we are aware of. So the chemical potential, which is the measure of the conserved quantum number, is additively conserved, right? I mean, the terminology comes from chemistry, chemical reactions. So for photons and Z naughts, you can emit and absorb them in any number if the temperature is high enough. So there is no chemical potential for photons. So for particles and antiparticles, it will be equal and opposite, because they can annihilate into these guys which have no chemical potential. So if you want chemical balance, the left side chemical potential must equal the right hand. The right hand side has got photons, no chemical potential. Therefore, the left hand side must add to 0. So if you have a finite chemical potential, that corresponds to an excess over particles over antiparticles, or vice versa, right? So there is some associated conserved quantum number, right? Now, the two gauge forces that we know of, electromagnetism and color, these are non-abelian forces, and they carry a appropriate associated charge. And of course, the most ancient is electromagnetism. So electric charge. Does the universe have electric charge? Well, you might be interested to know that there have been precisely 2 papers written on this rather, interesting subject, right? One was by Bondi and Gold back in 1926, I think, who basically pointed out that if the moon's orbiting around the Earth, and we know the strength of gravity, that if you don't want a electric charge from spoiling that, then that puts a constraint. Actually, they interpreted it in terms of a electron-proton charge difference, because at the time people were not even sure if the two have the same charge, right? And I mentioned this in a lecture at which Chiara Caprini, who was then a student at Oxford, was sitting, and she actually was working on the cosmic microwave background with Pedro Ferreira, and she immediately worked out in her head, well, hang on, we can improve that bound by about 10 orders of magnitude by looking at the acoustic waves in the primordial plasma at the time of recombination, which are also things in which you have pressure and gravity, right? It's the same kind of problem, and the electric charge would spoil things. So they actually improved the bound immediately. So this is a recent paper, well, recent 2005. But you see, just maybe you'll think of some other mechanism by which you can improve this further. Now, this is quite small, but it is actually not that small in the sense that at this level you would still have electric fields exercising an important effect on cosmological processes. So maybe one can constrain it further. Obviously, if you are the kind of person who thinks that the universe emerged as a fluctuation from the vacuum, it better have zero any conserved charge, right? And actually, the real universe is not far from that. The net baryon number is tiny. The net baryon number is one extra baryon for every 10 to the 10 baryon-antibaryon pairs. So this number we are going to actually measure from from primordial nucleosynthesis, but we are talking about a tiny imbalance. But that tiny imbalance is actually 1 billion times bigger than the expected thermal abundance of baryonic matter, as we discussed in Tracy's lecture. So it is, and that is the reason we are here. So we better take this seriously. And lepton number you would expect to be of a similar order, right? In principle, you could have a large lepton asymmetry in neutrinos because neutrinos are neutral. So the lepton, so the baryon number, this thing here, you would expect, of course, protons and electrons have the same charge as you have just seen. So you can't hide a large asymmetry in electrons, but you could do it in neutrinos. And that was, in fact, the subject of a lot of interesting papers in the early days. But when neutrino oscillations, large angle neutrino oscillations were discovered, then people pointed out that you would find it difficult to keep the asymmetry in just one flavor. It should leak out into the other flavors. And therefore, since nucleosynthesis is very sensitive to any asymmetry in electron neutrinos, because they are involved in the reaction that converts neutrons into protons, so you can put a very tight constraint on any asymmetry in electron neutrinos, and therefore, because of the mixing, also in mu and tau. So it's hard to hide a large lepton asymmetry. Now, in principle, the dark matter may actually also be a particle with a relic asymmetry similar to that of baryons, because if the dark matter carries couples to the SU2 anomaly, in other words, couples to the W in the same way that baryons and leptons do, it can actually share in whatever initial asymmetry there was. But we will not discuss that today. So let's go very quickly now through the thermodynamics of the early universe, which is trivial because it is particles, as was already discussed, they're in equilibrium, they're scattering much faster than the expansion rate, and it only takes a few scatters to come into equilibrium. You can actually do a numerical experiment to just set particle scattering and see how soon they develop the Maxwell-Boltzmann distribution. So for relativistic particles, we of course have the Bose-Einstein or Fermi-Dirac distribution, which is this, and we can integrate that over the appropriate thermodynamic quantity to get the number density, which is just the integral of the phase space distribution times the number of degrees of freedom. This counts how many, for example, for a photon there are only two states, although it's spin one, left and right, because there is no massive longitudinal mode. But for a massive particle in general, there will be 4 for a spin-half particle. And so there is a slight difference in the energy density for bosons and fermions because of the statistics, the plus and minus here. And similarly, for the energy density, you integrate over energy. For the pressure, you integrate over the pressure. Pressure, of course, is momentum, so that's what reflected here. And so you get some things that number goes as T cube, pressure and energy density go as T to the 4, and these are just some integrals which I've written in some notation, and these are basically all zeta functions. So they're just some numerical values. So for example, the number density of photons is 2 zeta 3 by pi squared times T cube, right? The 2 is for the 2 degrees of freedom. And when particles turn non-relativistic, so that this x is much larger than 1, the ratio of the mass to the temperature, then of course you have this Boltzmann factor that was also presented earlier. Actually, well, sorry I arrived late. Actually, my lecture should have come before yours. But so I'll go through this very quickly. I've already done this. Now, this is interesting. This was also discussed that the particles will stay in kinetic equilibrium. So there are two kinds of equilibrium we're going to talk about, kinetic and chemical. They are different. Kinetic equilibrium is equality of the temperatures. Chemical equilibrium refers to what I mentioned earlier, that the chemical potential balances out on both sides of the equation. Now, this is true as long as the scattering rate, which is some number times the cross-section averaged over the velocity, exceeds the Hubble rate. Hubble rate at this time is the square root of the energy density. Energy density is dominated by radiation, which goes as T to the 4, so it goes as T square. And the 8 pi g is basically Planck mass square, so therefore it goes as T square over mp. And this times a numerical factor, which can be not very big. It's of maximum of factor of 10. So the decoupling happens at the point when these two rates are equal. And at this time, if it is relativistic, then it would also have been in a chemical equilibrium, because it would have been annihilating into, say, photons, which carry zero chemical potential. So therefore, the particles and antiparticles would have equal and opposite chemical potentials. And its abundance will then just be given by the equilibrium formulae, right? Essentially, it will be the number density of photons times some statistical factor referring to whether they're bosons or fermions, and something counting the number of degrees of freedom, right? Now, what happens after decoupling? They are going to expand freely without interaction, so that their number is conserved, and their pressure and energy density are functions of the scale factor. No longer of the temperature, because they don't know about the temperature anymore. They have decoupled from the thermal bath. So, although they are non-interacting, their phase space distribution will retain the equilibrium form as long as they are relativistic. Okay, so energy and temperature have to both scale as 1 over A. Now, this simple fact appears to have been forgotten in a fair part of the cosmological literature, because, for example, we discussed neutrinos, which can have a mass up to, I don't know, the current upper bound on the neutrino mass from laboratory experiments is 2.2 eV. So it is quite possible that neutrinos, if they have mass, have actually turned non-relativistic long before today. And at that point, this distribution no longer holds. You cannot have an equilibrium distribution for a massive particle in an expanding space-time. It has to do with whether it has time-like killing vectors or not. But this fact is not particularly well known. So people continue to assume a Fermi-Dirac distribution for the decoupled neutrinos in certain situations when they should not do. But so please keep in mind, this is only true as long as they're relativistic. This was, by the way, done even by the WMAP collaborations. They were not quite aware of it. Of course, it doesn't matter if the neutrino mass is below today's temperature, which is 10 to the minus 3 eV, but otherwise it will matter. Now, as the universe cools below various mass thresholds, then the corresponding particles will become non-relativistic and annihilate. And this will create more photons, but it will not create any more of the decoupled particles, because they're decoupled. So the temperature of these decoupled particles will drop below the temperature of photons. T always denotes the temperature of photons. And the number density of these decoupled particles will therefore drop below the number density of photons. So let's show how to calculate this, and this goes back to a classic paper in 1953 by Alpha Folin and Herman. They said split the pressure into the pressure of interacting particles and the decoupled particles, right? And similarly the energy density. Now, the energy conservation equation then would, as before, tell you the amount of work that is being done by the expansion, in particular the pressure of the gas. So that is with reference to the temperature. These are for the particles still interacting, right? And that you can rewrite as d log A by dt. So 1 over A dA by, T over A dA by dt. So that's d log A by dt. You can write it as this, using the crucial fact that the number of decoupled particles is conserved in a co-moving volume. Now when you combine with the second law, then that gives you this interesting adiabat, as it's called, which is that log A equals, when you integrate it, log A equals minus log T, right? So A times T is constant if this guy stays constant. So this is the correction which takes into account how many particles are still interacting. And this is an important parameter which allows you to trace the thermal history of the universe through periods when the expansion is not adiabatic, when there are phase transitions or particles dumping entropy or whatever happens, right? You know, you might have some crazy idea that there is some parallel world with photons in that world coupled to our world, and so our photons can leak into that world. I don't care. Give me your crazy idea, I'll tell you how the scale factor evolves. The important thing is that remember that we don't directly observe the scale factor. For nearby objects, we can measure the redshift. When you go to the early universe, we have to somehow relate the scale factor to the temperature. We have to relate the time to the temperature, right? Otherwise, we can't tell the time. Because today, as you will see, we do have a measure of the temperature in the microwave background. So all we have to do is to relate the temperature of the microwave background today to at any time in the past precisely, taking account of everything that has happened. So, you know, so this is what? This is 65 years ago. You know, this has been around for a while, and these guys already told us what to do. So from this you can work out that if this chap is constant, for example, for a gas of blackbody photons, the energy density plus pressure by T to the 4 is just a number, because both of them are proportional to T to the 4. Then we have an adiabatic invariant. This is the source of the adiabatic invariant, right? But of course, there are epochs when the adiabatic invariance is broken. So let's see if we can relate them. For that, we need something which is conserved in a co-moving volume. If I know something is conserved, then I can keep track of everything, you know, anything else that happens, because I can, you know, basically it's like keeping control over your bank balance. So what is conserved? Well, money is not conserved, unfortunately, but but entropy is conserved, okay? So we have to construct a quantity which is conserved in a co-moving volume that will let us relate different epochs in terms of the scale factor, or rather in terms of the adiabat. The adiabat is the product A times T. That can change. So we have to keep track of that. So the entropy is pressure plus energy density over time, and we can write it in terms of the sum of the different entropy densities in the I species. So for each species, you know how to calculate that in terms of the phase space distribution. I already showed you this, right? And so you can parameterize Si in terms of the equivalent entropy for photons. So that just will then involve G, the number of degrees of freedom, divided by 2, because 2 is the number for photons. And similarly, this 4/3 factor is coming from the different statistics. So GSI therefore counts the number of bosonic degrees of freedom and the number of fermionic degrees of freedom. These are those zeta functions that we talked about earlier. So we can therefore calculate the total number of interacting degrees of freedom from here in terms of the sum of the individual degrees of freedom, right? This is just numerical, just bookkeeping. I'm showing you how to do the bookkeeping. So you can study it carefully later, so just follow the basic argument now. So similarly, I can write down the total number of degrees of freedom that contribute to the energy density. So analogously, I write for the total energy density in equilibrium. I parameterize that in terms of the photon energy density. The degrees of freedom I write in terms of the individual bosonic and fermionic degrees of freedom, and I add them up, and that tells me the total, right? So now we can do an exercise. We can calculate how the temperature of a particle which decoupled at some temperature, Td, how it relates to the photon temperature at later times. So at T less than Td, the entropy in the decoupled particles and the entropy in the still interacting J particles, which are the others, are separately conserved. So once the temperature drops below decoupling, the entropy in the decoupled I particles, right, which is here, that is now no longer in thermal contact with the decoupled D particles. So the two will basically evolve like separate universes. They don't know about each other. I mean, they're occupying the same space, but they are separate universes in the sense they have no thermal contact. But of course, the initial condition is that the two temperatures are equal at the point of decoupling. So if you solve these equations, you find that the temperature of the decoupled particle with respect to the temperature of photons is just given by this expression. Okay? Actually, this expression differs slightly from those in the paper I've cited here, because in fact you have to keep track of, there are possible situations where some particle decouples but then say immediately decays into something else, which is also a decoupled particle but has different degrees of freedom. So people think of all kinds of exotic possibilities, and so you have to have some framework that can accommodate everything. Now, after decoupling, the number of degrees of freedom that specify the conserved total entropy is then given just by the sum of the individual components, and so I can write it in terms of the number of degrees of interacting degrees of freedom plus some correction term. Okay? This just takes care of the fact that these particles no longer contribute to the entropy, but they contribute to the total energy density, right? Everything that has energy density gravitates, it's all to be taken into account. We don't care if these are hypothetical, I mean, these are non-interacting particles or interacting. So now we have a fiducial, we have constructed a total entropy density that is conserved in a co-moving volume. And so the ratio of the decoupled particle density to the photon density is just related to the value of decoupling. You just count the number of degrees of freedom at decoupling and at any other temperature, and that ratio is the one that will tell you the ratio of the number of these I particles to the equilibrium value, right? And always capital N is the number of photons in a co-moving volume. That's the fiducial. We are interested in that because that is something that ultimately you will measure on the sky in terms of the blackbody spectrum of the microwave background. So therefore, everything has to be normalized to that. Okay, so you can go through these things later. I can similarly parameterize the energy density by summing up the individual energy densities in the ith particle, and they are all going as t to the 4, and therefore this will be the sum of the bosonic and the fermionic. The 7/8 factor is to distinguish fermions from bosons. It's just statistics. The two terms come there. And so the relationship between A and T, now I can write as d log A by d log T equals this, rate of change of the interacting degrees of freedom, logarithmic rate of change of the interacting degrees of freedom. So in other words, the adiabat A times T equal to constant is altered by any change that there might be in the interacting degrees of freedom. So, everything is precise. There is no approximation here. So finally, we are in a position to calculate what is the time. So somebody asks you, what is the time? At what time did the quark-hadron phase transition or crossover occur? Now we are in a position to calculate it because we know the expansion law. Now this is in times of time, right? dA, so this is 1 over A dA by dt, and this, as I said, rho, we know how that goes. So we can just integrate that and get the value for the time in terms of the quantities that I have now substituted in there. So this will have this term, d log g interacting degrees of freedom by time as a correction factor to the usual one that you would have written down. So if this guy is 0, then we can integrate this very simply, and then we get that the time goes as 1 over t square, which is what I told you earlier. And in fact, the normalization is that at a temperature of 1 MeV, the time was about 1 second, because g rho was about 10, and this cancels out, so it's about 1. So that's simple to remember. Time was 1 second when the temperature was 1 MeV. So at a temperature of, what did I say, quark-hadron, 100 MeV, the time was 100 squared times smaller, okay? But so you would estimate 10 to the minus 4 is actually smaller than that because G rho has actually jumped by a large factor at that time. So we'll see how to do that more precisely. So it's not enough to just use this part, you have to also keep track of G rho. So we can work out when these events of some physical significance occurred according to what we know and also according to the extensions we might consider of physics beyond the standard model. So for example, let's go through the standard exercise of massless neutrinos. In the standard model, there are only particles which actually are stable but have decoupled from the thermal bath in the early universe and are still around are neutrinos. So they provide a useful test bed for our estimates. So the cross section for neutrino scattering is, maybe you already did this, is of course, we are talking about energies much smaller than the mass of the mediator. So basically it's just a 4-point coupling. The cross section goes as GF squared. GF is the coupling of that vertex, and times E square, but these are relativistic, so E is the same as the temperature, so it goes as T square, right? And the interaction rate therefore is T to the 5 because the number density is going as T cube, right? So therefore this is much faster with temperature than the expansion rate, which is going as T square. So you can read off from this that these two rates will be equal when the temperature drops to GF square times the Planck mass to the minus 1/3. So that's about MeV, right? And at this time, the number density of neutrinos, they're still in equilibrium, is 3/4 the number of photons because of the degrees of freedom and so on. And then the temperature here is just above the electron-positron annihilation threshold. So after that, the electrons and positrons will annihilate, and they will annihilate almost totally because there will be less, 1 electron in 10 to the 9 left over to balance the 1 baryon in 10 to the 9 because you must have electric charge conservation. And that will heat the photons, but it will not heat the decoupled neutrinos. So neutrino does not change, but the number of other interacting degrees of freedom decreases from the sum of photons and electrons, positrons to just photons. So it decreases from 11/2 to 2. Therefore, the ratio of the two is 11/4, and therefore the number density of photons at lower temperatures to the number density of photons at decoupling is 11/4. And that is just the ratio of these adiabat cubes, the ratio of the two adiabats, A times T to the 3, right? So you see, we have managed to keep exact track of what happened at neutrino decoupling and what happened subsequently. So if you ask me what is the number of neutrinos today at temperatures much smaller than ME, that will be 4/11 of the ratio of the number densities at equilibrium at decoupling, right? And that was 3/4, so this is therefore 3/11. So therefore, there are something like 410 photons or something per cubic centimeter today in the microwave background. So the number of neutrinos is 110, right? So we can tell that. We can say that with some confidence. And we can work out then the number of degrees of freedom that characterize the entropy density today, the energy density today, taking into account that the neutrino temperature is not the same as the photon temperature. It is smaller by that factor that we just worked out, 4/11 to the 1/3, right? And so you get some funny numbers here. But we know exactly what's going on. Incidentally, this is something that Tracy mentioned. When I say that neutrinos do not share this heat at all, that's not quite true because decoupling is not completely over. There is always some residual interaction between the neutrinos and the thermal bath. So when the electrons and positrons annihilate, a little bit of that heat does come into the neutrinos. So that's why the effective number of neutrino species is not 3, but 3 point whatever it is, not 4, something like that. Right? Yeah. So that is that. To get that, you have to do more work. You have to solve the Boltzmann equation and so on. Now, all we need to do to construct a thermal history is we have to count all the boson and fermion species which contribute to the number of relativistic degrees of freedom and take into account our understanding of any phase transitions. So this is from a recent paper. This is from these people who actually studied the quark-hadron crossover on the lattice in some detail. And what this shows is that the number of degrees of freedom, which is plotted on this vertical axis, jumps at a temperature of order 100 MeV very sharply, because this is the quark-gluon transition, and there are 3 colors, so suddenly a lot of new degrees of freedom have come into play. And therefore, this is particularly important, because if a dark matter particle is decoupling at around this time here, the number of degrees of freedom is changing quite rapidly, and that's when you have to use that machinery I've just told you. You have to be careful to work out what the abundance of dark matter is today. If it did it here or did it here, then it's much straightforward. Here it is not straightforward. You have to account for this curve. In the old days, we used to just draw some line at 150 MeV and in some MIT bag model, and then there was a 400 MeV line, and it was very uncertain. Now, thanks to these lattice people, it is now much more confidently established. So here is the number. Here are the numbers. So today, at very low energies, we have just neutrinos and photons. At 500 keV, we had electron annihilation. As you go up in temperature, you have increasing number of particles coming into the game. And when you get to the electric phase transition, so this was written at a time, this table is clearly from a time when we were not quite sure of exactly where the top quark would come at. The top quark is actually, they have just put an upper bound there, but now we know the mass. But it doesn't matter, because wherever it appears, it just contributes 4 degrees of freedom. The electric phase transition, incidentally, there is no change to the number of degrees of freedom, right? Because the Higgs, as you recall, contributes the longitudinal degree of freedom of the gauge bosons. So the total number of degrees of freedom remains invariant. That does not change. And so if you go up to very high temperatures above the electric scale, then the total number of degrees of freedom is of order 100. If you had minimal supersymmetry with the duplicating of all particles at that scale, it would have been 200. But so far, we know that is not the case, at least up to few TeV. Now, that is for the dilute gas. Sorry, there are some more remarks here. No, I think everything is clearly mentioned here, right? So this is for the dilute gas. Now, I should tell you that we are dealing with an extremely dilute gas. Even at the time of nucleosynthesis, people sort of think the early universe is a very dense place. That is true if you go to very early temperatures, but at the time of nucleosynthesis, the density of the universe, it might surprise you, was no more than the density of air in this room. Okay, that is why our job is so simple. We don't have to worry about many-body physics, all the things that Andre worries about. You worry about it. We don't worry about it. Okay, otherwise life would be quite difficult. Now, there are, after all, in the standard model, 2 things that we do have to worry about, which is the transitions from quarks to free quarks and gluons to hadrons, and the other is the electric transition with the Higgs mechanism occurs. Now, the Higgs mechanism earlier it was believed would be a first order phase transition, and it would indeed be so for a light Higgs. Okay, when people thought in terms of the Higgs being perhaps generated by the Coleman-Weinberg mechanism, it would be very, very light. And then you would have a first order phase transition with the generation of a lot of entropy and so on. But these lattice guys spoil all the fun, because they have calculated this precisely, and they say that for a Higgs mass which is more than this point here, 72 GeV, you don't have a phase transition at all. You're always in the Higgs phase, as it were. Okay, so you have to do this non-perturbatively, because the couplings here are quite large. So our naive idea of what a phase transition is not really relevant here. The endpoint is at this point, and so beyond something like 110 GeV, you would just have a crossover, and of course we know that the Higgs is at 125, so it definitely is a crossover. But this, remember, is in the minimal standard model. There could be new physics that changes the electric phase, transition, and indeed that is very attractive that it does so, because we have this experiment LISA, gravitational wave detector, which is going to fly, that will be sensitive to scales, which you can just work out now since I've given you the machinery. If you take the electric scale and you know its redshift, you know the temperature, if you scale it to the present day, you will find that it is of the kind of wavelength that LISA will be sensitive to. Okay, so LISA is like a hammer. We are looking for the nail. So we need some physics signals, and it is quite obvious that LISA will be sensitive to anything that happened that was interesting at the electric scale. But nothing interesting is happening in the standard model. So one more reason to hope for some new phenomenon that will give you a signal at this point. Anyway, all this was to impress upon you that we know everything about the early universe, amazing though it may seem, back to 100 GeV, right? Now that raises an interesting question, and this is something, again, one of my little interludes to hopefully surprise you. What is the highest temperature the universe reached? Any guesses? Anybody want to guess? Don't worry, I won't hold you to it. Any answer? Do you think the universe was as hot as the Planck scale? Right. Well, okay, let's do an estimate. Let's not speculate about it. So what we just worked it out. We have all the tools. So let's consider temperature set by the 2-to-2 scattering, right? So what is the 2-to-2 scattering rate? At sufficiently high temperatures, everything is relativistic. There is only one dimensionful parameter, which is the temperature itself. Right? So any scattering rate must go as some coupling squared by the temperature square. That is the only way you construct something with the dimension of a scattering rate. So the rate will therefore go as the number density, which is T cubed, times something that goes as 1 by T square. So it is going as alpha squared times T. Right? This is the fastest any rate can go. Of course, you can put in the strongest coupling you can find for alpha, which is the QCD coupling. So if you compare this to the Hubble expansion rate, and now I'm keeping track of all the numbers here, then the thermalization temperature cannot be any bigger than this quantity here. I'm just equating the two things. So alpha squared Planck mass divided by 3 root G star, and if I take a value for G star of order 100, then I get this to be 10 to the minus 4 times Planck mass. Okay. For that, I've taken the unified coupling, because the QCD coupling will run down, it's asymptotically free, and that is the asymptotically free value. And actually I've taken G star to be 200 to allow for the new physics. So it's 10 to the minus 4 of the Planck scale of MP, so in other words it's 10 to the 14 GeV. Okay? Universe could never have got as hot as the gut scale. This was actually quite a surprise to me when I first worked this out, because this is not what the literature says. The literature discusses baryogenesis at the gut scale, talking about particles which are in equilibrium and then went out of equilibrium and decayed, creating a baryon asymmetry. That could never have happened, because with the strongest coupling in the world, the QCD coupling, you could never have got hotter than 10 to the 14. Now, of course, that coupling does have a temperature dependence, so you can do this calculation more carefully. And in fact, it was done quite some time ago. And the precise answer is 3 10 to the 14 GeV. So you really have to revisit all these discussions of gut scale baryogenesis, and then there is this Kibble mechanism for topological defect production, monopole production, which says that at some time there was a temperature existed at the energy scales where topological defects were formed through some symmetry breaking, and you create one defect per horizon. That is implicitly assuming that there was an equilibrium state before that, before the symmetry breaking occurred. What this is saying is that above 10 to the 14 GeV, it makes no sense to talk about temperature at all. There is no notion of temperature. Particles don't scatter often enough to create an equilibrium distribution. So of course, the particles are still there. They have some distribution, but you cannot calculate that from simple thermodynamic arguments. You have to do much more work. I have no idea how to do it. Okay. For a weakly coupled scalar field, I know how to calculate, but for something which is medium coupled like this, I have no idea what the distribution would look like. So, so I hope this was new to you. Did all of you know this? No, you see? So there is something still to learn in cosmology. Okay. Right. Now, what is the evidence that we have that the early universe was actually in thermal equilibrium? I mean, all this I've been discussing using undergraduate thermodynamics, confidently writing down equations, but do I actually know that any of this was in fact the case? Well, nature has been very kind to us. the universe could have been a very complicated place, but in fact, it turns out that the relic radiation has a precisely thermal Planck law. I mean, it's amazing when you see imprinted on the sky some basic formula that you learned in undergraduate physics, right? It sort of makes you believe in something. that this did not have to be so. In fact, it is almost too good to be true. How is it that the spectrum of the microwave background, which as you know has a long history, it was first discovered through the radiation at centimeter wavelengths down here, at meter wavelengths, where Penzias and Wilson first measured it. So that actually is the original measurement of Penzias and Wilson. And now you have much more precise measurements which are going up the Rayleigh-Jeans tail up to the Wien peak. This is where most of the energy density is, and beyond it, right? And these little dots that you see there, those are the measurements by the Kobe satellite, which basically transform cosmology by giving us this spectrum. This, to my mind, is the first and perhaps the only example of what people call precision cosmology. This is precision cosmology because the error bars are, as plotted here, are about 20 times smaller than the width of that red line, right? Now, people say this is the most perfect black body in the universe. That is clearly not true. The most perfect black body in the universe was the internal calibrator in the Kobe satellite, okay, compared to which these temperatures were measured. But they took 5 years to calibrate that. So this data is from the first 7 minutes of Kobe. But in fact, to establish the precise value, 2.726 plus minus 0.002, that plus minus 0.02 came after calibration of the internal black body. And you can see that there is still room for possible distortions, which is a subject, another lecture, but basically it's a pretty good black body. And what this tells us is that the expansion was indeed adiabatic back to at least 1 day. Why 1 day? Because a day after the expansion, the universe became too dilute to form a black body like this. You can study the processes that form a black body spectrum that requires obviously creation and destruction of photons, because an arbitrary spectrum to convert to a black body which has a precise relationship between the number density and the energy density, you have to create or destroy photons, right? And so you need radiative processes. Radiative processes are inefficient and they shut off a day after the Big Bang. So therefore, this spectrum cannot have been created any later than a day. And at least that we know, therefore, that the expansion is adiabatic up to then. And by studying nucleosynthesis, we can show this holds further back to about 1 second. That will be what we discuss in the next lecture. So now we have this adiabat. So let us plot the adiabat. So this is the temperature. This is the scale factor, effectively. I've shown it as time. And A times T is a constant, right? That is this adiabat that you have just calculated. And now we can put on this the time, because we learned how to calculate the time. So therefore, starting from the Planck time, we have now worked out that electric Higgs symmetry breaking, etc., all that stuff happens around 10 to the minus 10 seconds. The quark-hadron transition happens around just 0.1 of a microsecond. Nucleosynthesis happening around between a second and a few minutes. Combination happens at I say combination rather than recombination, because the universe was always combined earlier anyway. So I mean, it was a plasma. So this is the first time it became neutral at few 100,000 years, and then fast forward, best part of 15 billion years to today, right? So we can use the black body temperature today, where we measured this black body temperature 2.726 plus minus 0.02. We can use that now as our clock, because we have learned to relate the temperature to the scale factor to the time, right? And therefore we can reconstruct our thermal history. Now in this picture, the furthest we can actually directly look back is up to this point here, because at this point the universe becomes opaque. It becomes a plasma. But we can, in principle, look back a little earlier to 1 second, in the sense that we can measure the elements that were synthesized then. And I'll show you in the next lecture that we can calculate that pretty well. And therefore, we are very confident of reconstructing our history back to about 1 second after the Big Bang. But we know that in principle we have a physical theory that lets us go back to 10 to the minus 10 seconds with some confidence, although there are, I mean, at some point we had to have created the baryon asymmetry. It's very likely that was the case that happened at temperatures higher than 100 GeV, because you at energies where baryon and lepton number could still have been violated by processes in the standard model, in the non-perturbative part of the standard model. But in principle, if you are very brave theorist and you want to write a paper claiming that you created the baryon asymmetry at temperature of half a second, in principle you could have done that. You could have done it here. So we can't really be confident about anything before nucleosynthesis. Apart from the fact that the variations that we see in the microwave background temperature at last scattering must have been generated much earlier. We don't know when, but at some point much earlier than that. So very quickly, already slightly over time, but I think it'll be good to sort of finish the bit about the CMB here. So how does the CMB actually, the last scattering surface form? So this is a standard calculation. I'll go through it because it is kind of emblematic of many other such rate calculation. So you have some Thomson scattering of electrons and photons, non-relativistic Thomson scattering, and the interaction rate is just the number density times the cross section. You have seen this before, and now I can write the number density as xc times t cube, xc being the ionized fraction, the fraction of the matter that is actually in the form of ions and electrons, right? Thomson cross section is huge, so this is a very fast rate. The expansion rate in the matter dominated era, by this time the universe is matter dominated, is h is going as t to the 3/2. So again, if this is less than h, the photons will decouple. When it is higher, there will have been an equilibrium. And at this point, this xc drops very, very rapidly because the temperature, at this temperature, the ions, the protons and the electrons combine to form hydrogen atoms, right? So at this point, this rate also drops very, very rapidly. So that is why you have a last scattering surface. Everything is dropping extremely rapidly, right? First of all, this is going as some high power, much higher power of the temperature than this. And secondly, the number of free electrons is dropping very rapidly. And this is important because if that last scattering surface was not very, very sharp, then it would be game over for the CMB. We would not be able to detect many of the things that we detect now. It would all have been subject to what is called silk damping and washed out, right? It would have been blurred. Now, the chemical equilibrium that is relevant here is that initially when this is in equilibrium, the chemical potentials of the proton and electron add up to that of the hydrogen, and now we know, since we know the number density of the hydrogen atoms in terms of the Saha formula, where this B is the binding energy, right? So the binding energy of hydrogen is 13.6 eV, and a question might arise as to why are we having all this at 1 eV rather than at 13.6 eV, because you might expect that as soon as the temperature drops to 13.6 eV or drops below that, then things can combine, right? Now this is because of a basic fact which occurs again and again, which is that the number of baryons is pathetic compared to the number of photons. So number of baryons by number of photons is, so this is the number that will actually work out. So this is something of order of 10 to the minus 10, okay? 5 times 10 to the minus 10. Why is this important? So we have this Planck spectrum, right? So the Planck spectrum is at some temperature T, but the average energy of the photons in the Planck spectrum, if you work it out, it is 2.7 times T, right? So if this thing is at 13.6 electron volts, right? I have photons of much, much higher energy here, which can still break up the hydrogen atoms. So I need to drop to a temperature which is sufficiently low that the photons in the Wien tail are not sufficiently numerous to break up the protons. Get it? Because this thing is dropping as e to the minus e over t, okay? So in other words, it's dropping exponentially, but it's something you should keep in mind is e to the minus 10 is 10 to the minus 3. So if I go 10 times in energy down the Wien tail, right, 10 times higher than the peak, the number of photons has dropped by a factor of 1,000. I have to go 30 times for the number of photons to have dropped by 10 to the 9. So actually I should have written 10 to the minus 9 here just to make it simple. So in other words, I have to go to an energy which is 30 times higher than the peak energy in order for the number of photons to drop to 1 part in 10 to the 9 of the number at the peak, and match therefore the number of neutral atoms that there are. Therefore, what will determine the temperature at which this process goes out of equilibrium is not the 13.6 eV, but 13.6 eV times the log of the baryon to photon ratio. The log comes because this is an exponentially falling spectrum. And that is reflected in the Saha ionization equation, which says that the ionization fraction will fall according to T to the 3/2 e to the minus b over T times this eta, which is the baryon to photon ratio. Same thing will happen at nucleosynthesis. So this is a sketch of how the ionization fraction falls very rapidly at around a redshift of 1,000, and this is where the expansion rate, the scattering rate and the Hubble rate are crossing. And if you calculate these temperatures is of order a fraction of electron volt. If you want to do this more precisely, there are codes that you can use to do that, which also take into account the fact that there is helium, that recombination is not just to the ground state but can also happen to higher states, and all those complications. Now, just one comment about fluctuations in the CMV. How do they arise? Very schematically, we are looking at photons which are coming out of a surface which has got some gravitational potential. So there are irregularities in this. These irregularities were imprinted long before recombination by some primordial process, call it inflation. And as the photons climb out of gravitational wells, they're redshifted or blue shifted. So something at the bottom of the well will obviously be redshifted as it climbs out. But interestingly, if the fluctuations are adiabatic, in other words, where there is more matter, the photons are also more compressed, right? Because the ratio of baryons to photons is constant. Then the photons would also have been hotter at the bottom of the well. So you see, this effect cancels this effect, right? Fortunately, they don't quite cancel. 1/3 of the effect is left over. So because these effects don't quite cancel, and then there is a little effect due to the Doppler shift because these peaks are not actually static, they're moving, they're acoustic waves. Because these two effects don't quite cancel, 1/3 of the effect is left over, and that is very fortunate for us because that means that there are fluctuations on the last scattering surface, right? Otherwise, there would have been nothing for us to see, okay? And because they don't cancel, the CMB actually carries a memory of the past. Because recombination is so fast that is not smeared out by successive layers, it is a very fast event, and therefore we can actually see a lot of structure in the CMB. And those fluctuations, as you know, the so-called Rosetta Stone of cosmology, have transformed the subject in the last 10, 15, 20 years. Actually, it was in the 80s that it started. And now we have a complete picture of how these fluctuations have grown under gravitational instability in the dark matter that we actually infer from this picture must dominate the universe, because the time between here and here is not enough for structure to grow from the fluctuations that we see here. They should have started growing earlier, a factor of 10 earlier. And the way that happens, therefore, is schematically that we have some initial early state, we have some process that generates these fluctuations, and they grow from recombination till the present day. Just you can treat it by first order perturbation theory in GR, and the parameters that govern it are the cosmological parameters of your model, including, for example, matter density, radiation, baryon density, any neutrino fraction, if any. And these photons then free stream, they inhomogeneously stir into anisotropies. So the parameters here are the redshift for reionization, which will again smear out the perturbations corresponding to that scale, the horizon at that scale, and equation of state of dark energy if it exists, and so forth. So we have a complete picture of how this happens, and therefore I can end on the slide that all the big labs in particle physics have now on their websites to impress upon the public that what they're doing is actually investigating the history of the universe, and that is how starting from the Big Bang, therefore there are these hypothetical epochs, Planck wall, grand unification, etc. But then the quark-hadron transition, and then the formation of the elements, formation of atoms, formation of stars, galaxies. But you see these numbers that they're put here for the time, that comes out of the calculation that you have just done, right? So you can believe this poster, although it is pretty, it is actually quite correct. Okay, all the numbers are correct, but you have to do quite some work to get this. And of course, this is, every major lab is doing this because this is a much more compelling way to convey to people the excitement of particle physics than trying to tell them about scattering amplitudes, which are a little harder to absorb, right? So I think I'll stop here and carry on in the next lecture. Thanks. Okay, 10-minute break.